What I want to cover in this session is the concept of recirculating conveyors. What is the idea here? Let's look at this example. It gives you a good idea of what do we mean by recirculating conveyors. So here we have PCB as our entities. They come to the system, they come to the receiving, and then they go to conveyor 1. And they get moved on conveyor 1 till they get to the first assembly person. On conveyor, then in the assembly 1, they go under the assembly, and then they are put on conveyor 2 to go to the next step. So let's assume these PCBs, these entities, only need to get processed on assembly 1 or assembly 2. They are doing the same thing. If they come on conveyor 1 and assembly 1 is busy, they automatically go to conveyor 2 and they continue till they get to assembly 2. Okay, so if assembly 2 is busy as well, they just continue recirculating on the conveyor till they finally get processed in one of these assemblies. That's why it's called recirculating conveyors. Okay, so if the part comes in, it only needs to get processed on assembly 1 or assembly 2. If any one of them is busy, it passes and goes to the next one. So if let's say if it gets, however, if let's assume it gets processed on assembly 1, then it just passes assembly 2 and then it gets shipped. Okay, so when the parts gets processed on assembly 1 or assembly 2, then the parts go to the PCB ship and then from there gets shipped. If a part gets to the PCB ship and it has not been processed on assembly 1 or assembly 2 yet, it goes to conveyor 4 and it gets recirculated. Okay, so that's the whole idea behind this, and it's the case in a lot of manufacturing processes. So these are the type of systems that you may very well end up modeling at some point in your career. A couple of things about this model. The entity that comes to the systems are PCBs, and they come to the system with inter-arrival time of 15 minutes, exponentially distributed. And the processing time on assembly 1 or assembly 2 is exponentially distributed with average 10 minutes. They are the same operation. As I said, the part needs to get processed only on assembly 1 or assembly 2. The processing time on each one of them is exponentially distributed, average 10 minutes. When the parts come to the PCB receival, so we have some processing time. That one has normal distribution with average 5 and standard deviation 2. This one. And also when the parts get to the PCB ship, it also has some processing time, and that has normal distribution with average 10 and standard deviation of 3. Okay, and one thing about the conveyors is that each one of these conveyors has the length of 100 feet and speed of 20 feet per minute. That's what we know also about each one of these conveyors: length of 100 feet and speed of 20 feet per minute. Also, all the locations here have capacity of infinity except assembly 1, assembly 2, and PCB ship. These 3 locations have capacity of 1. They can process 1 entity at a time. Assembly 1, assembly 2, and PCB ship can process 1 entity at a time. However, the rest of the locations have capacity of infinity. They can hold infinite number of entities. So let's create a new model in the folder for week 11. Name your model as PCB Electronics Recirculating Conveyor. Here I have the name. PCB Electronics Recirculating Conveyors. Name your model as this. And please create the locations, create the entities, create the arrival, and we do the processes together. Okay, so here's my locations. All the locations with the capacity I mentioned. Only assembly 1, assembly 2, and PCB ship have capacity of 1. The rest have capacity of infinity. For all the conveyors, also use the first in, first out rule. So do not change that rule. All the conveyors have capacity of infinity. And also for each one of the conveyors, make sure that the length is 100 and speed is 20. So please make sure this setup is the case for all the conveyors here in this model. length of 100 feet and speed of 20 feet per minute. Okay. My entity is PCB. And for the arrival, entities go to PCB receive one at a time from the start of the simulation for as long as I run the simulation. And inter-arrival time is it 15 minutes? Let me make it 15. Inter-arrival time is 15 minutes. Okay, for PCBs, exponentially distributed. Now we go to processing. Okay. So for processing, our entity, which is PCB, which is currently right now as at PCB receive, from there, where does the entity go from PCB receive?
Conveyor 1.
It goes to conveyor 1. So the processing time at PCB receive has normal distribution, average 5, a standard deviation 2, and that's the processing time we are going to put here for the PCB receive. And from there, they go to conveyor 1. Okay. Next entity that is now at conveyor 1. So what happens at conveyor 1? Where does the entity go? They go to assembly 1, assembly 1 is idle. And then if assembly 1 is busy, then they go to conveyor 2 and from there to assembly 2. Okay, so then I need to check something. I need to put the condition. When they are in conveyor 1, I have to check if assembly 1 is busy or not. If the assembly 1 has capacity to process a part, then the part goes to assembly 1. Otherwise, it goes to conveyor 2 and goes through the rest of the process. So here I need to check the free capacity on assembly 1. Is there any free capacity in assembly 1 to process a part? If yes, send the part to assembly 1. If not, send it to conveyor 2. So the way to check this, the command to do this check is free cap. When I say free cap and then the name of a location, it returns free capacity on that location. So here, assembly 1 has capacity of 1. So if assembly 1 is not working on any part, free cap assembly 1 returns 1. So let's say here, assembly 1, let's say has capacity of 1. So in that scenario, assembly 1 has capacity of 1. If I just say free cap assembly 1, let's assume if assembly 1 is not processing a part, free cap assembly 1 will return 1. That's the free capacity on assembly 1. However, if assembly 1 is processing a part and is busy, then the command free cap assembly 1 would return 0 because there is no free capacity on assembly 1. Then it will return 0. Okay. Let's assume assembly 1 has capacity of 4. And assembly 1 already is processing 2 parts. So let's assume assembly 1 has capacity of 4 and is already processing 2 parts. Then if I call free cap assembly 1, what would it return?
2.
It would return 2. It has capacity of 4. It's already processing 2 parts. So the free capacity is 2. It will return 2. Okay. There is another command that potentially we can use here. That command is contents. Contents. So when I write contents of a location, it works basically opposite to free cap. Free cap returns free capacity. Contents returns the capacity that is busy. So for this, let's look at the same example. I have assembly 1 that has capacity of 4. Okay. Let's assume assembly 1 is processing 3 parts right now. Okay. So I have assembly 1 that has capacity of 4. And let's assume assembly 1 is processing 3 parts. Now, if I call free cap assembly 1, it will return what value?
1.
It will return 1. It has capacity of 4. It's processing 3 parts. The free capacity is 1. Free cap assembly 1, it will return 1. But if I call contents location, it will return the number of capacities that are busy, the number of entities that are there, the content of the entities on that location, the number of entities that are there and are being processed. Then if I call contents assembly 1, it will return 3. Okay. So both these comments, free cap and assembly and contents, they return something related to number of entities that are being processed and the number of free capacity that we have at that location. But just know how you have to use them. So both of them basically can help us here. So either I can say if free cap assembly 1 is 1, which means the assembly 1 has 1 free capacity, then send the part to assembly 1. Or I can say if contents assembly 1 is 0, which means there is no entity there. The content is 0. There's no entity there. Nothing is being processed there. Then send the part to assembly 1. Okay, so both of them work, but and you can use any one of them that you like, but I want you guys to be mindful about what each one of them means so that you can use them correctly. Okay, I'm going to use free cap here. Okay, here I'm going to write the condition. So I'm in a conveyor 1 and I want to check if assembly 1 has a free capacity so that I can send the part over there. If free cap, you see it turns blue, it's a keyword. If free cap assembly 1. So if free cap assembly 1 is 1, that means assembly 1 has 1 free capacity, so it can process the part. Then what happens? Free capacity on assembly 1 is 1. It can process the part. Then what should we do?
Route 1.
Then send the part to assembly 1. And if I can potentially put that as the first possible route for this entity. So then send it to assembly 1. So I can consider that as the first possible route. So that's going to be route 1. Else, if free cap is not 1, which means there's no free capacity, then I have to send the part to conveyor 2. So that's going to be my next possible destination. Conveyor 2. What is the thing I have to do here to make sure?
Start a new block.
The same block.
I have to make sure it's a new block.
New block.
Yeah, I have to make sure it's a new block. So always, when I want to refer to these routes here through the if then else command, through a code I write in the operation to say, if this condition holds, go to route 1, go to route 2, go to route 100. Always, I have to make sure these are separate blocks and I have to make sure they have the right numbers so that I can refer to them correctly here in the code. Okay, so if free capacity is not 1, which means there's no free capacity on assembly 1, then the entity has to go to route to the conveyor 2, and conveyor 2 here is in route 2. Okay, make sure to save, guys. Okay, next. Let's assume PCB ends up at assembly 1. Here in assembly 1, the processing time was exponentially distributed, average 10 minutes. Wait 10. Okay. And where do we go from assembly 1?
Over to.
We go to conveyor. Because even if when it's processed in conveyor in assembly 1, it can't just immediately go to exit. It still has to go through the conveyor till it gets to the PCB chip and leaves the system. Okay, so even if it gets processed in assembly 1, it still has to go to conveyor 2. Okay. Next. Oops. PCB. Okay. And if it goes directly to conveyor 2, I mean, it's already in conveyor 2. Okay, so we are now going to take care of the second one. So now we consider the scenario that entity is in conveyor 2. No matter if it went from conveyor 1 to conveyor 2, or it got processed in assembly 1 and it went to conveyor 2. So we are going to consider all of those possibilities. Now, let's assume the part is in conveyor 2. What is going to happen here? Part is on conveyor 2. What are the things I need to check?
Are we assuming this part didn't get assembled at assembly?
That's one of the things I have to check. I can't make any assumption. I have to just check that. So that's one thing. When I'm in conveyor 2, remember for the conveyor 2, one of the possible destinations is assembly 2. But a part gets to assembly 2 only if it has not been processed on assembly 1. That's one condition. What is the other condition for the parts going to assembly 2?
If assembly 2 has a free capacity.
Exactly. So the part goes to assembly 2 if the part has not been processed on assembly 1, and also if assembly 2 has capacity to process a part. If assembly 2 is busy, the part is going to pass assembly 2 and just go to conveyor 3 and then recirculate. So a part goes to assembly 2 only if those two conditions hold. Okay. So for a part that is on conveyor 2, then one possible destination is in assembly 1 under those two conditions that I mentioned. And if those conditions do not hold, then the parts go to conveyor 3. Okay, so let me write down. So for the part that is conveyor 2, the two possible destinations, either the part goes to assembly 2 if those two conditions hold, or if the part goes to conveyor 3, directly goes to conveyor 3. And I want this to be a new block. And I'm going to write down here on the operation under what conditions I go to route 1 and under what conditions I go to route 2. Okay. So for a part that is on conveyor 2, we said for the part that to go to assembly 2, I have to check two conditions. One, if the part has been processed on assembly 1. Second, if the assembly 2 has free capacity. So the free capacity part is easy. So free capacity assembly 2. So if assembly 2 has free capacity and both these conditions have to hold, okay? Now, if assembly 2 has free capacity and the part has not been processed on assembly 1, can you give me some ideas how I can capture this part in the model? How can I somehow check if a part has been processed or has not been processed on these assemblies?
We can either assign it, we could give it an attribute, or we could convert it to a different entity if we wanted to.
The tag things would be a lot easier. So let's do the tag. So the idea here is that, okay, I give a tag. When the entities come to the system, I give them a tag. When the entity gets processed on any one of these assemblies, I change the value of the tag. So when the entity gets to a location where I need to check if the entity has been processed or not. All I need to do is to check the value of the tag. If the value shows that specific values that corresponds to it has been processed, then the part has been processed, and you just take the right action at that time. Okay. So I want to assign a tag to all these entities that come to the system. And when the entity gets processed, I need to change the value of the tag so that I know this is the entity that has been processed. So let's go to the attributes. Here I have a tag. I have called it PI indicator. You can give it any name that you like. It's going to be an integer. I'm just going to give it two possible values for representing not being processed and being processed. So it's an integer. Okay. So let's define that attribute. Now, remember, what is the default or initial value of all the attributes?
0.
It's always 0. Okay. I can keep that initial value, and when I get to assembly 1 or assembly 2, if the part gets processed, I can change the tag to 1, for example, and consider tag 1 as an entity that has been processed, and just go from there. Okay. And that's perfectly fine. Just for the sake of learning, I'm going to do it a little differently, just for the sake of learning. Otherwise, what I just said is perfectly correct. Just for the sake of learning, let's go to arrivals. And right here in the logic, I can change the value of the attribute right there. So right here, I say, okay, as soon as these entities are created and they are arriving to the system, right there, change the value of the attribute. So here, for the value of the attribute that is by default 0, I want to put the value of 1. So in the logic, in the arrival, you can do that. So right now, so in this scenario, entities are created. As soon as they arrive to the system, the value of their entities is 1. So all the entities that are in the system, their default value for their entities is not 0 anymore. It's 1. Okay. And again, we do that just to learn that this is also possible in ProModel. So then the default value is 1, then 1 corresponds to an entity that has not been processed. When I go to processing, right here, I can change that attribute, the value of that attribute. So if a part has been processed, then I can change it to 2, 3, 0, anything that I want, anything other than 1, to just represent that any value other than 1 represents an entity that has been processed. So where should I do that change? Where are the places where I have to change the value of the attribute if it has been processed?
Assembly 1 after it is processed.
Assembly 1 and assembly 2. So let us go back to assembly 1. If a part gets processed on assembly 1, after the wait operation is done, then I also need to change the value of the attribute. So PI, I'm going to, let's say, put value of 0. And 0 means part has not been processed. I just put a comment so later I know exactly what the 0 and 1 means.
So doesn't 0 mean that it has been processed?
You are right. Yes. 0 means the part has been processed. Thank you. Yeah. We process, we change the tag to 0, and 0 means the part has been processed. Okay. So now when a part leaves assembly 1, the tag has changed. So I can check that anywhere in the rest of the process to see if that part has been processed. Okay. Now let's go to assembly to conveyor 2. So now here I want to check if the assembly 2 has free capacity, if free cap on assembly 2 is 1, and also I want to check if the part has not been processed. What do I need to put here? If the part has not been processed.
PI equals what?
PI is 1, because PI is 1 means part has just entered the system. Remember, in arrival, we change the attribute to 1. That means the part has not been processed. So PI1 means the part has not been processed. If free cap is 1, assembly 2 has a space to process another part, and PI is 1, meaning that the part has not been processed, then send the part to assembly 2, and that's route 1. Else meaning that either assembly 2 is busy or the part has been processed already. Then then send the part to conveyor 3, which is route 2 here. Okay, make sure all of your routes have their own block number. And make sure you save as we proceed. Okay. After conveyor 2, okay, let's assume PCB, the PCB ends up in assembly 2. Here, we again are going to perform the processing, 10 minutes exponentially distributed. What is the next thing I need to do here in assembly 2?
Change the tag.
Change the tag to 0, meaning that the part got processed. Okay. And from assembly 2, the part goes to conveyor 3. Now, the part goes to conveyor, the part that is already at conveyor 3. At conveyor 3, I'll also do similar things. So at conveyor 3, one possible option is to, if the part is done, it has been processed in assembly 1 or assembly 2, and also if I have free capacity at PCB ship. We want to check that. If I have free capacity at PCB ship and the part has already been processed, I send the part to PCB ship to be shipped. If that's not the case, if PCB ship is busy or the part has not been processed yet, then I send the part to conveyor 4 to gets recirculated. So then at conveyor 3, I need to check again. If I have a space on PCB, if the part has been processed. Second, if there is a space at PCB ship to ship the part, then I send the part to PCB ship. Okay. So then one possible destination for me is PCB ship. And if that's not the case, then I send the parts to conveyor 4 to get recirculated. And one other possible destination is conveyor 4. And I make sure this destination is a new block. So then when I'm at conveyor 3, I need to write the condition again. If the part has not been processed, if the tag is 1, let's do that. If the part has not been processed, okay, if the part has not been processed, I want to send it to conveyor 4. What is the other condition under which I send the part to conveyor 4?
PCB ship is busy.
If PCB ship is busy, that means free cap is
0.
0. Okay. So if the part has not been processed, PI equals to 1, or it's not and, or. So if even if one of these conditions holds, I send the part to conveyor. If the part has not been processed, or free cap on PCB ship is 0, no free capacity, then exactly we go to conveyor 4 to get recirculated. So I'm going to route 2. Else means the part has been processed and free capacity is 1. Then send the part to the ship. So send the part to route 1, and let's now here, let's assume PCB ship ends up at, let's assume PCB ends up at PCB ship. What happens over there? We just have the processing or the wait time, which is normal, average 10, standard deviation 3. And that's it. So, and then that's the processing time at PCB ship till we are done with the shipment. And then the part goes to exit from there, leaves the system. And if PCB ends up at conveyor 4, where do we go from there?
Conveyor 1.
We go to conveyor 1 for the recirculation. Now, when the part gets recirculated, and let's say the part gets to conveyor 1, now, do I need to add anything to the condition here? Let's assume this is the first part that entered. Initially, remember, all I needed to do on assembly 1 is to check if the part if the assembly 1 has free capacity or not. That let's assume was for my first part. And I know that part has not been processed. So the part gets to assembly 1. All I need to check if there is a free capacity on assembly 1 or not. But now the parts goes through the process and now gets to conveyor 4.
You need to check the attribute. You need to check the tag.
I need to check the tag. Why do I need to check the tag?
Because that part could have been processed already.
That part could have been processed. And then what is the reason that it is recirculating?
PCB ship was busy.
Yeah. So if we face a scenario that the part has been already processed on assembly 1 or assembly 2, however, since PCB ship was busy, the part was sent to conveyor 4 and it's going to get recirculated, then I don't want the part to get processed again. Okay? Then in that scenario, I have to make sure when I get to any one of these assemblies, I have to check if the part has been processed, don't do anything on it. I already put that card for condition for assembly 2, but remember initially we didn't put that for condition for assembly 1. So let's go back to assembly 1 here. And let's go back to conveyor 1 here. And in conveyor 1, previously I only checked if assembly 1 is available or not, but now I also have to I have to add one more condition. If assembly 1 is available, and also if the part has not been processed. And PI is 1, meaning the part has not been processed, then send the part to assembly 1. However, if you come to conveyor 1 and the part has been processed because it's a recirculating part, then even if assembly 1 is idle, then don't do anything. Just send it to conveyor 2, let it circulate again till finally it's out of the system. Let's run this for 2,000 hours. Okay, I have about 8,000 PCBs leaving the system. And here you can see the percentage of time in operation or utilization of assembly 1, which is more than assembly 2, which means when the parts are in the conveyor, most of them gets processed on assembly 1 and leave the system, and then some of them also gets processed on assembly 2 as well. Okay. Now, what I want you guys to do is to tell me how many parts get recirculated here. So I want you guys to define a variable and tell me how many parts get recirculated in this model. How many parts, so basically what I mean is that how many parts leave the system in their first run. They go through conveyor 1 and then 2 and then 3 and then leave the system. but how many parts end up getting recirculated? So how did you guys deal with this? So we want to count how many parts got recirculated. So we define a variable, let's say. I'm going to call it, okay, so I'm going to define a variable. I'm going to call it recirculated, and it's going to be an integer. Okay. Process. Where did you start increasing the value of this variable to count number of parts that were recirculated?
Conveyor 4, anything that hits conveyor 4 is going to be recirculated.
Okay. So here at conveyor 4, because anything that is going to go to conveyor 4 definitely is going to be recirculated, right? So at conveyor 4, here I can say increase this variable. Then what is the issue related to this? So what for the value that we get, why that value is so high? So what is the thing that here we are not calculating correctly? And remember, I want number of parts that were recirculated, not how many times I go through the recirculation.
If same part gets recirculated multiple times.
Yeah, so in this way, if the same part gets recirculated 10 times, I'm going to count all of them here. However, that's not what I want. I want number of parts that got recirculated, not how many times I went through the recirculation overall. So what is your suggestion? If I just want to count number of parts that got recirculated, how do you think we have to do that? So I can assign a tag to this entity. And when the entity gets to conveyor 4, I can look at the value of the tag. Let's say I define a tag, let's say. Circulating tag. Okay, so I'm going to call it circulating tag. So I give this tag. So when the entity gets to conveyor 4, I'm going to say for circulating tag, add 1 to the value of the tag and save it here, save it in the tag. And then if it's for the first time, if circulating tag is 1, then increase the value of the variable that is going to count recirculated. So I define a tag, and this initial tag for the initial value of the tag for all the entities is 0. When the entity gets to conveyor 4, I start increasing the value of the tag. In the first value that the tag is going to get I'm going to increase it by 1, so it's going to be 1. 1 means that's the first time that this entity is going to recirculate. Okay. Now, and that one time, I want to increase this variable that counts number of parts that have been recirculated. So if the value of the tag is 1, then increase this variable that is recirculated. And let's assume the part goes through the whole conveyors again and comes back again. And again, it's not going to exit the system. It's going to be recirculated for the second time. The part gets to conveyor 4. And here, I'm going to increase the value of the tag. Now the value of the tag, I'm going to add 1 to it and save it in the tag. So the value of the tag now is going to be 2. However, here, I increase the value of the variable recirculated only if the value of the tag is 1. Now the value of the tag is 2. Okay, fine. Let the part go through the recirculation, but I'm not going to increase the variable that counts number of parts that have been recirculated. Now that we are here, before we run it again for 2,000 hours, let's calculate work in process again. So go to variable, define a new variable called work in process. Where is the right place to start increasing that variable? Before wait or after wait?
Before.
Before. We want to start increasing work in process. And where is the right place to decrease it?
Shipping.
add PCB chip. When the part is done, I'm going to decrease working process. I'm going to run it again. So in this results, the total number of exits that we got is about 8,000, and the number of parts that got recirculated is about 5,000. And the working process, the number of parts in the system, number of PCBs in the system is about 6.3 that are somewhere in the system, either being processed or somewhere on the conveyors.